Willkommen im AI4EU Café. Wie immer begrüßen wir erstmal alle Teilnehmer und auch unseren Sprecher heute. Das ist Miai Datu. Aber wir fangen langsam an, weil die Teilnehmer kommen jetzt erst. Der Titel heute ist Earth Observation Big Data Challenges, the AI Change of Paradigm. And as I said, Miai Datu will be our speaker. He's from German Aerospace Center, DLR, in Oberpfaffenhofen in Germany. Not so easy to say. And my name is Carmen McWilliams. I'm always your moderator and organizer. Myself, I'm a director of Grassroots Arts and I'm partner in the European AI4EU project. And I just always want to tell you that we are recording this session. This is a live session where we will later also put the recording on the platform. And please, no confidential information shall be shared in this cafe session. In this cafe, the speaker can express their personal view and opinion. This is not necessarily the official AI4EU project opinion. And also for you who may want to know what is actually the AI4EU Café, the AI4EU Web Café offers a series of live web sessions open to the public. The Café is an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. And this is an interactive session. As our speaker is live, you can also ask after the presentation questions. You will find on the right side a panel, and there you will see the titled questions, and you can type them in if you like, and we will read them after the presentation, so I can answer them. But you can also, if you want, after the presentation, raise your hand. There is a hand button, and if you want, we can also give you the mic. So now, again, I want to welcome our speaker. It's a pleasure to have you here, Miai. Thank you. And I will now introduce your CV. Miai Datu received the MS and PhD degrees in electronics and telecommunications from the University Politehnica Bucharest, Romania in 1978 and 1986. And in 1999, he received the title Habilitation à diriger des recherches in computer science from University Louis Pasteur, Strasbourg in France. Currently, he is senior scientist and data intelligence and knowledge discovery research group leader with the Remote Sensing Technology Institute, IMF, of the German Aerospace Center, DLR, in Oberpfaffenhofen, and professor with the Department of Applied Electronics and Information Engineering, Faculty of Electronics, Telecommunication and Information Technology, UPB. From 1992 to 2002, he had a longer invited professor assignment with the Swiss Federal Institute of Technology, ETH Zurich. From 2005 to 2013, he has been professor holder of the DLR CNES chair at Paris Tech, Paris Institute of Technology, and Telecom Paris. His interests are in data science, machine learning, and artificial intelligence and computational imaging for space application. He's involved in the big data from space, European, ESA, NASA, and national research programs and projects. He's a member of the ESA Big Data from Space Working Group. He received in 2006 the Best Paper Award, IEEE Geoscience and Remote Sensing Society Prize, and in 2008, the National Order of Merit with the rank of Knight for outstanding international research results, awarded by the President of Romania. In 1987, the Romanian Academy Prize Traian Boia for the development of SAADI image analysis system and activity in image processing. So he is IEEE Fellow. He is holder of the 2017 Blaise Pascal Chair of CEDREC CNAM CNAM. So now, after this introduction, and I see we have a lot of participants on air. Thank you for everybody coming. And I will hand over now the mic as well as also the control to Mihai. He will make the presentation himself. And again, enjoy. I will do it now. I've changed the moderator. Mihai has now the control. You can do it now, Mihai. And
thank you, Carmen. Thank you very much for making this webinar possible, organizing this very well. Hello, everyone. Thank you for attending. So I would start now. I share the screen with the presentation.
I see it well, no, Mihai? I see it well. I think everybody sees it super.
Presentation models. Okay. So the today topic, it's Earth observation, big data challenges, the artificial intelligence change of paradigm. So I would start with an acknowledging my colleagues at DLR in the Data Intelligence and Knowledge Discovery team, to acknowledge the Chaire International for Blaise Pascal in Paris, and the CEDREC Research Center for Informatics at the Conservatoire National Art and Métiers, Unique Aerospace, a cooperation of DLR with the TU München, and also my colleagues in the team of Research Center for Spatial Information, Geospace Tech, at University Polytechnic in Bucharest. I structure the presentation in, let's say, 3 parts: an introduction, presenting actually the main reasons, the background of the use of artificial intelligence in Earth observation and the specificity. Later, I go over the challenges, exemplifying solutions which have been provided. And in the last part, I go to the newest development in artificial intelligence with very specific, very particular solutions, problems, challenges for satellite imagery. In the beginning, I will start with a 1-minute movie for which we would like to acknowledge ARD and Arte, the German national television channel, Arte is a German-French television channel, and also Professor Peter Baumann at Jacobs University, which made possible this movie. It's 1 minute from a longer movie, which is available on the internet. I'm using this 1-minute movie to present actually which are the objectives of my team. So which are the objectives of big data to solve problems in Earth observation. So we have many sensors in space. The sensors, they are Earth observation, but also planetary astrophysics. These sensors in space, they are equipped with a multitude of instruments. The data, the signals recorded by these instruments are downloaded, transmitted to Earth. So this is a digital library of DLR, and the instrument signals are transformed by computation in images, satellite images. This huge volume of data, it is stored in big archives. This is a 50 petabytes archive of DLR, storing satellite images in the beginning of remote sensing in the 80s up to now, and continuing storing this, and preserving, perpetuating for long term this huge value in information. However, this data is digital. It's difficult to access it. The objective of my team, my colleagues, is to transform the digital data in meaningful, easy to understand. So it is a PhD in an immersive environment, computer reality like, and we project the images in the cave in 3D, and when the operator is looking at an image, the system understands, it's a machine learning, the system understands how to project this data and where we have to look to discover our meaning. So it's a new kind of artificial intelligence projecting big, two-dimensional spaces in such a way to become semantically meaningfully easy to understand. So I use this movie to make the introduction of subjective. So we need to develop algorithms, but also systems and tools which to transform digital data, which is specifically acquired by sensor instruments, which is different from other kinds of data, in full information for the users. And one of the particularity in Earth observation, it is the divergence of the thematics. So compared with many other fields, Earth observation is covering a multitude of fields. I present in this slide only 6 of them, probably a little bit more particular. Everyone knows about application of remote sensing in agriculture, in ocean, in forestry, urban monitoring. So in here, I actually underline the climate change, which is a major impacting application of observation, and object recognition, damage in infrastructure, deforestation of the mining or illegal mining, which are again extended field, so only to show the diversity. So we have to face many use cases, many user perspective conjectures in to make value of the data. So Earth observation, it is a convergence of technologies.
May I just interrupt you for 1 second? May I? Maybe we need to put the video out because the audio is not perfect. Maybe your video, can you maybe, I think it gets better with audio if you just click on this video button.
I need to identify the video button.
A video button is like on the right control. You don't see it? Okay, then just continue. I'm sorry for interrupting. I was just like.
Yes, no. I'm afraid not to touch the wrong button, so I'm not very much used to the interface.
Just continue. Sorry for interrupting. It's fine.
Okay. So I'm back on the slides. So Earth observation, it's a convergence of technologies. So actually, satellite images, they cannot be interpreted without having knowledge about the mission, about the orbit, the time of acquisition. The sensor, the mode of the instruments on satellite platforms, they are complex. They can work with a various resolution or in different spectral or polarimetric setups. We need to know the control of the mission, how the acquisition is planned. We need to know the ground segment, how the satellite data are processed, which are the parameters in the processor, because they depend on the performance of the products. Definitely, we need information platforms to distribute the data. Something happened, and to make it available to the user. And definitely, we need to have the method of science and the application methodology integration of values. So Earth observation is a complex technological convergence, and the challenges which arise in artificial intelligence for Earth observation, they refer to mission intelligence, sensor intelligence, data intelligence, application intelligence, business intelligence, and they cover all the from the user, their data, sensor, mission, and the architecture of the mission. So this was the first conclusion, and I will further elaborate on this. I'm going now to present these challenges with results obtained recently in a research or a technology project. So the sensor intelligence. So in here, actually, we have the following example. We have the Copernicus Sentinel-1, the synthetic aperture radar, which is illuminating with microwave scene like the urban area, receiving the echoes back and generating a satellite image. That is called a monostatic radar image. However, the echo on the buildings or infrastructure can be received on a set of antennas, which is on the roof of the university. So this set of antenna gives a diversity in the information because it's a diversity in the geometry of the phase. This diversity from the set of antenna can be further exploited by, let's say, modern signal processing like compressive sensing, deep learning, and we can obtain a new information. So in here we have all chain from mission orbit, because we have to know precisely the orbit to process to understand the signals, configuration of the antenna, which is the sensor itself, and all the methods which deal with artificial intelligence up to getting new kind of information, extending, adding new value to the transmitted signals by the mission. So the first example, it is computational imaging. So artificial intelligence is broadening Earth observation because of this convergence of technologies to many fields. Computational imaging, it is one example. So in here we have the example of bistatic, previously presented, where we receive echoes transmitted by the satellite with a ground-based antenna. We can combine these echoes also with a ground-based transmitter antenna, and we obtain new kind of products, a new kind of information, which is increasing the value of the satellite mission. Formation flying. So today we talk about constellations and also formation flying. So in here we extend the idea of using the radar, the sensor, in a different way. Satellites flying together, they communicate, they have radio links. In this project, we use a radio link to determine, to measure the relative position of the two satellites. The precise position, the knowledge of precise position of satellites is very, very important, because we can, with this, simulate instruments in space which cannot be implemented on a single platform. They are too large for this. So in here we have an example of using the communication, and in a cooperation with GMV, we did a test on simulating the platform satellite in the advanced robotic test bed. Satellite images, they are never interpreted by themselves. We need measurements in situ to validate, to calibrate our data. We need measurements in situ in such a way to enrich, to complement our data. So we have networks of sensors, and today sensor networks are very, very spread around. So Internet of Things is one of the examples, and social media, social networks or GPS information, which are complementing and enriching the satellite information with punctual and very, very complementary information. So in situ data utilization is one of the major desiderata objectives in the Copernicus programs. So we integrate all these signals from satellites for heterogeneous sensors on ground with maps or other kind of information models in platforms. These platforms, they are advanced IT technology, including visualization, database, communication, processing, artificial intelligence, and they enable user to access in an easy, automatic way the content of the information. So we change from data access to information content, to semantic, to knowledge. Definitely in the last few years, the attention was attracted in the field of artificial intelligence by deep learning. However, deep learning in Earth observation has a particularity. It needs to be a physical deep learning, because we want to extract not only the objects in the satellite images, we want to extract the physical meaning, like signatures, physical parameter observed by a polarimetric sensor. So here the polarimetric data is transformed in features which are representing physical quantities of the observed land cover. So data must be presented to users, to people, in a very easy way. So big data transformation information needs a communication channel to the user. That's visual data, visualizations of data is very important. So we need to present simple, understandable abstracts of our data. And visualization is helping to do this. So we can examine large volume of data in visual way, in very easy way to be understood. So as a summary, the Earth observation data intelligence has to deal with all the processing from the sensor model to the Earth observation system, to the semantic knowledge extraction, to human machine communication, data fusion from various sources, data mining, discovery, search engine querying for information, the calibration, and the data model of the product. So data intelligence, the same as observation, it is a field of convergence of various technologies in the field of science. So just to stress on this aspect, artificial intelligence and observation has to deal with mission intelligence, like orbit, configuration of the satellite platform, sensor intelligence, data intelligence, application intelligence, business intelligence, and discovering the entire chain, user, data, sensor, mission, and mission architecture. So I go now to present a selection of the most important challenges. So the first challenge is the multi-sensor and multimodality nature of the data, which is to be processed, to be analyzed in Earth observation. So data is multispectral, so invisible like RGB, but also going far to infrared sensor. Synthetic aperture radar with various polarization, with various wavelength from X-band 3 centimeter, C-band 5 centimeter, L-band 20 centimeter, and soon to P-band about 1 meter, but also other kind of instruments like radiometer, altimeters, only to very few of them. Earth observation, they are coming not only with a signal, like the image, they are accompanied by metadata. We cannot understand this if we don't know the location, the time, the instrument parameter, how the signal was acquired, orbit information, product processing levels. Satellite Earth observation data, it's almost never interpreted in isolation. Always user they recall geographic information system or maps, like various thematic maps like vegetation topography, which are coming in a different digital format with textual descriptors and model evaluation. So satellite images need to be integrated with in situ information, either Internet of Things. So here we have diversity of large sensor networks, measuring air, water content, or in situ photography, measurement of physical parameter. Location, multimedia local awareness, GPS taking spatial context are additional information which helps and enrich the Earth observation data. Internet and social networks and mobile communications, they are a fantastic evolution. So recently, in the last 3-4 years, they become and complement fantastically the Earth observation. So all these challenges actually they are mapped in the design, the need to have design of systems which are able to integrate all this data. Integration means from the understanding of the different file format, but also the data fusion, the machine learning, which is able to learn from various heterogeneous sources. So I have to enrich the Earth observation with information which is coming from a different source, complementary. So in such a platform, and here, for instance, we integrate Lucas, which is a European database. Every 3 years, operators they go and take pictures in a grid of 2 by 2 kilometers, indexing the pictures. So there are pictures north, south, east, west, indexing the picture with GPS location and with metadata. So this database is updated every 3 years. It's a huge value for Earth observation and many other applications. So this information in situ photography, it is integrated with Earth observation products and also with other third-party services like maps. So this is an example of integration of GIS and Lucas database in a system where one could make a data selection, a query for various semantic category of land cover agriculture crops, like vineyards or corn, and making a change analysis over the period of observation, in this case, just 3 years, 2009-2012. This data is further integrated with multispectral, in this case, a worldview, and the TerraSAR-X, very high resolution multispectral and SAR data. And they could become verification, training data, but also object data fusion in such a way to have more information, more precise information extracted from the data. So we need to make scene understanding. And in this example, I go from an observation, a single observation, synthetic aperture radar. In this observation, we have 2 similar objects, 2 bright parallel lines. We observe the area with a multispectral sensor. In the multispectral sensor, the scene is the same scene, looks different. We have, instead of having 2 parallel bright lines, which computer vision will decide they are similar objects. In the optical data, we have two parallel bright lines, which looks like a highway or a bridge. And instead of having bright two lines, we have only dark line. If we have the map, on the map, we identify the bridge and the highway. So understanding the fusion of this data and the machine learning should clarify, should reveal the semantic of the object. However, one of the objects in the map is not present, but we have a picture from this point in this direction, and this picture reveals the nature of the object, this one, which is a power line support for the railway. And the double line in here, it is not an object. The double line is a signature, the reflection of the microwave on this metallic part, and a double reflection on ground and back to the satellite. So satellite images are not images. They are doppelganger of the reflection on the scene. And we need to invert not from the image to the object, but from the image to the scattering phenomena, to the signature, and from signature to identify the object. So it's a different problem with many other problems in the image or computer vision. So semantic extraction. So definitely computer vision and pattern recognition are fields which are enriching Earth observation. However, we have specific tasks in semantic description, and these are mainly quantitative measure and physical meaningful parameter extraction. Compared with picture photography by any camera, in the sensor, in the satellite images, we have these signatures, and we have physical quantities like quantity of crop, biomass, chlorophyll, or the temperature of ocean. Because of the nature of the multimodalities of the sensors, we need to deal with the problem of registration. Registration refers not only among satellite images, it means registration with other in situ information or other sources of data. And at the end, we need to deal with the fusion of information from various structures. And we need to deal with huge variability of scene and classes. So these are some challenges which have to be faced. I give an example now with a satellite image time series. So satellite image time series are now probably one of the most successful products of Earth observation. So after 30 years, 40 years of satellite observation, and with the continuations, a new sensor, Copernicus, we can observe almost every site on Earth for a long period of time. So this is a Landsat time series in Bucharest, 84 to 2012, from 120 images. This series was continued recently with the Sentinel data. So these data tubes of data, they contain huge information of high complexity. So patterns are not anymore lake, forest patterns, they are in 3 dimensions, they're evolution patterns. So a pattern, it is a change of a natural landscape, construction area in an artificial lake. Pattern, it's a change of construction area in a parliament palace in Bucharest. A pattern, it is all the object is 3D, spatial and temporal evolution. Pattern, it is spatial change from agriculture to a residential area. Again, space and time. All these patterns, they have value when they are correlated with external data. So we correlate with demographic information in the area, and we can make prediction, which is very important in urban planification, for instance. It is just one example. So sensors in space, they are beyond visual perception. So sensors like multispectral, they have street channels like RGB, where you can understand the image like a water body and vegetation of the border. However, these sensors, they have information in other 10 bands that are going to infrared. Visual interfaces, they can use only 3 bands RGB, and RGB is confusing. And we need to develop like a deep sensors, artificial sensors, which are transforming the multispectral channels in a RGB visual image, but preserving similarities and dissimilarities. So in the RGB, these 3 objects, they are different. They have different colors. However, the sensor with certain bands tells that they are very similar. And here, this 13 bands image was transformed in a 3D, in a 3 channels information, which preserves the similarity. So these areas, they are basically similar. In RGB, we can have areas which looks like being similar in color. However, in reality, in the multispectral data, they are different. So this kind of sensing is a kind of microscope which is transforming non-visual data in something visual. And that is very important for all systems because we have to operate the system with graphical interfaces. I have an example of transforming low resolution like Sentinel at 20 meter in a high resolution sensor. So we trained networks with TerraSalix data and we transform 20 meter resolution in 6 meter resolution data. So it's another kind of transformation of the data, which is very important. So this is a kind of sensor, artificial sensors transforming and enriching the information. We go now to the problem of semantic relationship. So in text, we deal with documents described by word. And doing the analysis of the words, we can understand the topic in the document. We apply the same technique in such a way to fill the semantic gap in between the satellite images and the computer, the algorithmic processing. So we extract words in terms of signature polarimetry. In this example, we apply a latent directly allocation, a generative model, and we obtain new classes, new topics. So new topics, they reveal parameters of the land cover, which otherwise they are not visible in a classical approach. These methods, they are further developed on a Boltzmann machine going in the field of deep learning. So we are at the edge of maybe revolution in technologies, quantum resources. So quantum intelligence, it's referring to Earth observation with resources like sensor, computational imaging, quantum sensor. And we have access already to quantum computing, quantum machine learning, and quantum signal processing and information theory. So all these aspects are now under investigation as I prepare the next generation of tools and technologies to better exploit big heterogeneous data from Earth observation. This is an example of a roadmap. So starting with the Earth observation problem, we are now investigating phenomena in quantum like entanglement. We identify particular cases, there's a phase unwrapping, and we make design of quantum synthetic aperture radar, and we make studies for environment using existing quantum resources. And this is a planning for the future. Human understandable artificial intelligence. So artificial intelligence should extract patterns which are understandable. They must be presented with adaptive and natural user interfaces. The learning process should anticipate the user behavior, and the learning process should be a collaborative one, should be a dialogue. So we need to understand the user intention, the context of the application that is established by interfaces, which is a perform a dialogue. So this is an example of interface and the machine learning behind, which when clicking on the screen with a mouse, we define the water body, and the system is recognizing and bringing all images with reverse. So with such a technology, we make query by image content like finding rivers, urban houses surrounded by forest, railway infrastructure. So system is adaptive, does not involve any pre-classification, it's adapting to what the user search. During this search, the user also can discover structures. Satellite image time series, they need more advanced interfaces because you need to deal with temporal evolution, but also with a spatial evolution. So we need to combine the spatial temporal patterns and to define new kind of categories and classifiers. We need advanced visualization in which people that can immediately discover the model of the data, how the data is grouping in such a way that can better understand outliers or the classes before doing machine learning. It can also verify machine learning and classification procedures. All these methods, which are reflected in implementing algorithms, they have to be implemented in tools and platforms. So these tools in this moment, they are web-based, they are distributed because today, the modern data, they are open and free. They need to be time relative to the interactions with the operator. So the operator should click on the image and get a result in seconds. They are based on cloud computing that go to be a strongly federated system. And the trend today is to take advantage of the evolution in the knowledge technologies developed by the blockchain. Example of our system, it is Earth observation image librarian, EODIB, which is data mining and knowledge discovery, in which at DLR for the ground segment of TerraSAR-X, we integrated the red modules in the ground segment, existing ground segment, with the HAL directly in such a way to have the algorithms close to the data, the big data, and providing tools like indexing the data, relational database, query by image example, and advanced semantic understanding of the data. With these tools, we could index a database of 300 cities all around the world, obtaining 1,300 semantic levels. And later with statistical methods, analytical method, we can characterize a city. So we have quantitative information, semantic and quantitative, like a fingerprint of a city, or we can analyze jointly various regions of the Earth, so finding common patterns in between various urban settlements. Satellite image time series. So it's a TerraSAR-X time series after the tsunami in Sendai in 2011. So the understanding of the time series itself, it is beyond the visual perception. We need to transform, to extract the classes, which again, they are spatial temporal classes, which have quantitative characterization of evolution in time, and a class, which is actually a data cube itself, should be categorized semantically and represent the results in a simple way, like data analytics, agriculture before the tsunami, destruction and recovery, airport recovery, flooded areas and how they mitigated, aquaculture destructed. So we need to synthesize information from big data in simple analytical format to be understood by the users. Visual data mining is one of the tools which allows to discover actually particular patterns. So many times clusters, compact clusters like forest or agriculture, they are not so important as outliers. So important things, important parameters, they could be in these outliers. Patterns like this, which show a different projection of the data set, because the data set is multidimensional. A single projection is not always relevant. They show again the behavior of the data, and that can also be used for verification of clusters and the accuracy. Mainly because in Earth observation, the reference data set is very expensive and very limited in size. So we go now in exploratory visual analysis, in which I explain how to use virtual information and autoencoders, deep learning, to transform the data. So in here, we transform the sensor 13 bands in 3 bands in such a way to preserve similarities, dissimilarities, which are beyond the visual perception. So we develop methods based on classical virtual information theory, communication channel, and also with the autoencoders, so enhancing the performance of visual data. Synthetic aperture radar, it's far to be considered an image. Synthetic aperture radar, it's a bidimensional, two-dimensional representation of echoes reflected by ground structure. So synthetic aperture radar are actually signals modulated to amplitude, frequency, and phase. We cannot see it. So synthetic aperture radar also has a very particular property, among others. It's just an example. So taking the spectrum of the data and extracting a subband, we obtain an equivalent antenna. So we have a physical meaning in the data. So the Fourier transform is related to the look angle of a virtual antenna to the scene. So in these radar images, we have objects like this, which we can encounter in many places, and we need to verify if they are really identical or not. And we develop methods which are transforming the data in space and time, and we can identify if the objects are different or not. So the movement is not a movement because of the movement of the object. It's a movement which actually reflects the change of the phase and frequency. Comparing this signature can understand if images are representing similar or dissimilar objects. We have also particular properties of the sensor. So here I choose an example from Iconos. In the multispectral image, we have this configuration of vehicles on the highway. The panchromatic is the same vehicles, they appear in different configurations. The sensor has a switching time. So it means we have an interesting parameter in the sensor data, the time, which could be used to extract additional information. In Sentinel-2, observing planes, they have a strange behavior. They are decomposed. It's again a parameter of the sensor, which is important in information extraction. The Tandem-X, it's a formation flying in which we have a diversity in the satellite position. We have a baseline in space and a baseline in time. Using also the properties of the synthetic aperture radar, like azimuth multi-looking, we can obtain information for ship detection and velocity estimation, which otherwise cannot be. So in here, we are using full information about the orbit, formation flying geometry, and the parameter of the sensor and the sensor mode is a way to extract information, which otherwise from a single sensor be extracted. So that's an example in which, like a parallax, we can demonstrate the detection of the speed of the ship. So we go now deeper in the deep learning. So deep learning, it is a field which is today extremely popular. So in the last year have been published every month more than 500 papers on deep learning, only in deep learning. So it's a huge investment in research and trying to find application and new ideas in the field of deep learning. So here proposed a framework for content-based image retrieval in deep learning, in which we have to deal with feature extraction, similarity metric, having the relevant feedback to implement a dialogue in such a way to make the best selection of paths in the satellite imagery. So the feature extraction, which was a classical approach in any image interpretation, including verse observation, so extracting like multispectral signature, polarimetric signature, structure, texture, geometrical parameters, is now replaced by deep features, which are extracted by deep architecture, like a CNN. Deep architecture also, which they have to deal with feature coding in such a way to have a much better recognition of the complicated patterns which appear in satellite images. Deep features, they need fine-tuning, changing from a sensor, from a data set to another set. The model must be updated, and fine-tuning is a technology which is really very valuable in Earth observation, because it could actually take advantage of limited training, which again in Earth observation they are very expensive and very small compared with computer vision, and yet maintain very good performance of the models. So this is an example on the database UCD method, in which we have the features which they are colored according to the labeled data. So the database has 21 classes, each class has 200 optical imageries. After applying a deep learning, that begins to be grouped somehow, and after fine-tuning, the feature generating, they are almost perfectly grouped. So it was an example of influence and benefit of fine-tuning. We go now to deep learning, converting them from classifiers in segmentation. So very high resolution satellite image, they need really image segmentation for application like cartography. So here actually we exploited knowledge about the nature of the image. So we know that objects, they are characterized by borders, by edges. And here we ingest edges in the network enhancing the performance. So this is a building ensemble which was segmented with a classical CNN and with a CNN which was boosted by injecting the edge information. So it's evident on the parking lot that the segmentation of the car is much better. So existing information we know about should be injected in the network. We need to take advantage of the knowledge we have, the models we have about our scene or the data. And having this concept in mind, we go now to explainable deep learning, in which we develop methods to extract physical parameters. We take advantage of the knowledge of the physical models because we know about the sensor, polarization, wavelength, incidence angle. We know sometimes properties of the object or models. We know the image formation, like double bouncing, specular backscattering, and we want to learn from all these phenomena in such a way to have a better identification of the object. So we want to disconnect from methods which are applied for object recognition and inject existing knowledge, physical model, in such a way to understand complexity of the Earth observation data. So in here, we work on polarimetry. So we are learning the classical polarimetric signature, like multiple volume surface scattering. Knowing them, they also have quantitative descriptor, low, medium, and high entropy. And we train networks with polarimetric data, and we apply the data to dual or single polarization. We obtain now signatures from the single or dual polarization, which in the past have been possible to be obtained only from the full polarization. So the model is generalizing and extending the physical scattering and extracting this for single polarization data. We go further and exploit the basic property of the synthetic aperture radar of the spectral analysis, which is equivalent to a different antenna. So cutting the spectrum and doing the Fourier analysis, we obtain like different antenna looking to that. So we make the short time Fourier transformation of the data. We obtain multidimensional signature. And based on this signature, we demonstrate that they are characteristic for various kinds of buildings, and we integrate this in the network, and we enhance the prediction of the data for urban areas, for urban classes, which have difference in scattering with 7%. So we can enhance the recognition of urban man-made objects. Definitely, if the scattering is uniform, diffuse in all direction, like it was water or agriculture, or in the case of forest, we do not have real enhancement. This property doesn't exist. However, for objects, structure, with have these directional properties, we can enhance and extract the information. So I will conclude now, letting some time for questions. So today in, let's say, big data and artificial intelligence, we rely mainly on areas emergent under the data science, artificial intelligence, and information architecture. So the frame today was mainly to bring intelligence to the data, so bringing the algorithm to the data. So it was a concept which in the past few years was the most important concept in all fields of data, big data, not only Earth observation. So in Earth observation, actually, as a trend, it is now to go from the data to go to the sensor, to the source of information. So this means computational imaging, computational sensing, so moving the intelligence to the sensor in such a way to enhance the amount of information the sensor can capture and potentially reduce the data volume, preserving the information and even better information, and also the methods of artificial intelligence and machine learning to be explainable. So have an explainable intelligence in such a way to extract information which is pertinent, physical parameters, quantitative parameters, and also to extract this information and qualify, give always a measure of trust. It's not enough to have a classification of the image. It's not enough to have the quantitative evaluation of a biomass. It's important to give a trust interval for the measurements, mainly because we deal with remote sensing, where we do not have access to for the verification. So I'm concluding now the presentation, and I look for questions.
Yes, thank you, Mihai. Thank you very much. And thank you for this fascinating presentation. I think you have to press on the camera. I cannot activate you. If you want to be back, you have to press on the left camera button.
Yes.
Yes, thank you. So it's much more personal. Thank you. Okay. Wow, it's fascinating. As I have so many questions myself. So I'm the moderator and organizer. I start first because what are you working right now on, and which project? What are you doing exactly, and what would you like to do next?
Good question. So in this moment, I would like to take all this body of knowledge developed with a team, with the colleagues for my PhD, because it's very important to have people which have knowledge in this field. And definitely continue as a part of deep learning artificial intelligence, like algorithms, to be developed and to be used for Copernicus, for European satellite platform, to extend this from synthetic aperture radar and multispectral Sentinel-1 and 2, which are medium resolution, high resolution, to go also in deeper physical parameters like Sentinel-3 and 5, and also to go to the X-Explorer, because in there we have really completely different approaches which are behind the integration of gravitational data. This could help a lot in understanding seismic, which is complemented by interferometer. But also, meanwhile, to go to new concepts in which to make design of intelligent missions. Also, because at this moment, having a mission in space, the small satellites, nanosatellites, is a technology available at hand. And almost every university could have a configuration of satellites and make experiments and demonstration in orbit with new artificial intelligence. So artificial intelligence involved, it is one of the objectives.
Okay, thank you. So I encourage the audience and the participants to also ask questions, because my second one is, I know from our last meeting in Venice, in our AI4U meeting, you said you are really interested in other people working on similar projects and similar work. What are you looking for? I would contact you. What are you looking for? Other researchers, scientists, or maybe even users, or people who are you looking for? Somebody
for everything which is enthusiastic on this topic. So I start with the users. I believe in this moment that Earth observation could broaden the application. And the application might be completely surprising us at this moment. Definitely for this is needed that knowledge about Earth observation data and information is penetrating in other communities. So definitely probably closer to the Internet of Things, but also social media, exposome, like Maladi's extension, because mainly fields which they require global observation and also observation for a long period of time. Because satellite observation is, for the moment, the only global, periodic, and long-time observation.
Okay. Yes, and now I have Alessandro Safiotti, our partner in AI4U. He has a question. Thank you. Fantastic talk, he says. Fantastic talk. So a compliment to you. You know that AI4U has an open call for challenges. Are you planning to submit any of the challenges that you listed in your talk? It would be so nice.
Yes, yes. And definitely I would like to do this, and also to try to stimulate PhD students and young researchers to contribute to this. Yes, for sure.
Great, because as I heard in Venice, you shall do it for the first challenge soon. It's until the middle of March, no? So, and then for the audience who has no clue what we're talking about, we are having open challenges, and very soon after the challenges are clear, we're going to have open calls. there are SMEs, organizations, research, universities can apply for even single researchers for these open calls. And there will be another cafe session just about open calls. So as soon as we're coming close to the open calls, there will be one, and you will see, and you will get an invitation. I have another question. Is this data which you are now, we understand, is this really available for a city, for public universities, schools? Can anybody access this data? An artist? Yeah, I cannot mention them all. A commercial company.
Yes. So the Sentinel data, the Copernicus data, it is open and free. So ESA already put it at disposition all the tools and system to access the data, and everyone could access the data in any quantity it's willing to process. And that is another point of change of paradigm. So this was not the case a few years ago. So satellite images have been generated. Now, free data, open data, that in principle should be a huge impact on its developer communities, researcher, because many ideas could be developed to have that material, the data is there, and also that it's a chance for application. So to spread, to enrich the application, to discover new fields, to valorize the satellite acquisitions.
Yes, yes.
So again, open data, it is a fantastic opportunity in this moment at global scale, because it doesn't refer only to Europe, it refers to all the world.
Yes. Yes, I just got the same question from Martin Hesselmeier. Thank you. I know him personally. He's from Germany. This and it's the same question: is the data open? And so there are these questions. And I would say whoever has interest, because we are ending very soon this session, but there are so many questions that you may directly write to MIAI. If you have more questions, as well as to me, I can also forward it to MIAI. And please feel free to ask these questions. And it would be great also if you participate in the challenges, which are soon coming up. But in order to be now on time, I want to thank you very much, MIAI. And it's totally fascinating. I myself am thinking what I want to do with the data. So I will come up with my own ideas. And as all the time, I will now introduce shortly the next presentation for next week. And also feel free, of course, if you want to be one day a speaker, just drop me a message. The next live cafe session will be on February 5th, next Wednesday. And this time it has a question as a title. It basically says, are non-diverse AI research and development teams risking bias in innovative algorithms and artifacts? The speaker is a lady, Huma Shah, a researcher from Coventry University, UK. So I'm very happy to welcome her next week. And you will get automatic your invitations. If anybody wants to drop out of the email list for this cafe, just also tell me and you're out at once. And again, thank you everybody. And this was very fruitful, and bye-bye. Yeah.
Thank you. Thank you. Thank you and goodbye.
Good night. Goodbye. No, not good day.
Goodbye. Bye-bye.